I hope that the last chapter went really well for you. We covered one-dimensional motion using these kinematic equations. If you do not feel like you've mastered this really solidly at this point, I would recommend that you reach out to one of the course instructors or your lab instructor or a tutor and get really awesome at these as soon as you can, because this next chapter builds on that stuff. And it can be a little rough if you're still shaky with this. Okay, so with this in mind, for 1D motion, what we're going to do now is move into 2 dimensions. So what that means in terms of physics and our math is that when we go into 2 dimensions, each of these quantities that we've looked at before, the final velocity, the initial velocity, the acceleration, and the displacement, now they're all vectors. So they're vectors, so we can break them down into their component form using a Pythagorean triangle. So if I were to think about a projectile, which I've shown here in purple, and the total net displacement here, I'm showing with the R vector, I can break that down into the X and Y components. And of course, since that's a right angle, I can use the Pythagorean theorem to relate those things. We can do this with all of these vectors. All of these can be broken into their X and Y components. Let's look at V0. So I've shown, again, the same picture of my projectile in purple, and V0 there, that's my initial velocity, and it would be given an initial velocity, and often, but not always, we're given an angle as well. I can take that velocity vector and break it down into its initial X and initial Y components. And again, that's a Pythagorean triangle. So I can use that equation to relate them. I'm gonna note one more thing that we can do with this, and we'll do this a lot with the initial velocity, but we can really do it with any of these vectors. If I look at this triangle, I can say that the cosine of theta is the adjacent over the hypotenuse. So let's look at our triangle. That angle, the adjacent is V0x, and the hypotenuse is V0. So that's how I get this. I can multiply, looking at the far left and the far right, I can multiply both sides by V0, and I can get V0x is V0 times cosine theta. We can do the same thing with V0y. V0y is opposite the angle, so we'll be using sine is opposite over hypotenuse, V0y over V0, and I can rearrange that and get an equation. If I have V0 and theta, I can calculate V0y and V0x. Now, I'm gonna note something. Don't memorize these and just always use these, because these are dependent on this triangle. If we were given a different angle, let's suppose I was given that angle instead, and there is my V0y and my V0x. X is now opposite and sine is adjacent. So you have to be careful and look at your triangle. Okay, so we broke down X and Y, and V0y and V0x. We can do the same thing. It's a Pythagorean triangle. I just don't have a picture of it, but this is for the final velocities. So the final velocity in the X direction squared plus the final velocity in the Y direction squared has to equal the net final velocity squared. So I know this is a lot. We're repeating the stuff we did for one-dimensional motion, but we're getting it doubled now. So we're gonna have all of these values, displacement, initial velocity, final velocity, acceleration, and time for X, and we'll have them all for Y. There's one variable that appears in both columns. Do you see it? It's time. time appears in both columns. And so often you're going to see these projectile motion problems called time of flight calculations, because a general, not always, but a general strategy is we'll use Y information to get time to bring it over here and find something about X, or in the other direction. Maybe we'll use X information to get time to come over and solve for something in Y. All right, so what happens to our kinematic equations, right? Our one-dimensional kinematic equations become doubled. So I have X ones and Y ones. They're the same equations, it's just these are all X and these are all Y, because I have to have it in component form. I can't put vectors into those equations. So I have a note here to be sure to view some additional resources that you can find in Canvas. One of them takes you to an iBook on projectile motion that goes over all the conceptual things in a different way that I have already stepped through. And there are 2 videos that explain the changes in velocity as a projectile goes through its motion. And I haven't done that and don't plan to do that in this intro, but this has 2 videos that are helpful. Okay, some common pitfalls. Don't assume that cos goes with X and sine goes with Y. I know I just said that a moment ago, but it's really easy to do. You need to always look at the triangle and figure it out from the trigonometry. If the projectile isn't symmetrical, be careful about assuming things. So a really common assumption people make is that it's at the peak at the halfway point. So for this one, if it took, say, 5 seconds to do this entire time of flight, that would happen at the 2.5 second mark, right in between. But if the projectile is not symmetrical, so here it starts up higher than it ends, that we can't do that. We can't just take that in half. Quick note, don't forget to pick an origin. All right, now I have some remember. Now, these were in the book and in some of the videos, but when you see in problem solving the word dropped, the ball is dropped or released, that means V0 0, V0 X, and V0 Y, all 0. If something is hit or kicked horizontally, I kick a soccer ball off of a building, that means that V0 Y is 0, and whatever the V0 is V0 X, because we can't really make a triangle out of that. Gravity always X down, so it should have a negative sign. And if an object ends up at a lower height than it was started at, which is kind of my picture over here, Y, change in Y will be a negative value. In this picture, if I look at that vector where it is below the x-axis, that lies in quadrant 4. There is a video that goes over that reviews your quadrants in case you need to watch that. But this is in quadrant 4, so V0 X is positive and V0 Y will be negative. All right, one last thing that's a remember. So what I've sketched here is a projectile, and there are 2 videos that go over in more detail than I'm going to right now, that go over how the velocity changes as a projectile goes through the air. But when it's over here, V0 X and V0 Y are both positive. When it's at the very top, the velocity in the Y direction is 0. There's an instant where it's 0, just like in the last chapter. But Vx is positive, and it's actually equal to V0 X, provided our acceleration is 0, which, unless we have a motor on the thing, or I have wind resistance, air friction. Unless I don't have those situations, which are uncommon, the velocity in the x direction is whatever it was initially. And then finally over here, when it lands or right before it lands, Vx is still positive. In fact, it's still equal to V naught x, and Vy is a negative value right before impact. And so this chapter we're doing just like last chapter, we're talking about after something is moving, describing its motion right up until impact. So we're not including, if you had a ball go up and fall, of course it's gonna land there and it'll have a velocity of 0. But when a question asks what's the final velocity, it's really asking the velocity right before impact. All right, well, I think you have some concept questions to practice with, and then we'll move on to problems.